Okay, so welcome back to the lecture series on electromagnetic waves. So in the morning session, we have discussed about Faraday's law. Okay, and we have seen one Maxwell's equation, that is del cross E equal to minus dou V by dou T. Okay, so this is one Maxwell's equation we have seen, and we have seen that for time varying case, okay, I mean the Maxwell's equation has been changed. Okay, for the static field, the del cross E was 0, whereas for time varying case it is minus dou V by dou T. Okay, so now we'll try to investigate one more Maxwell's equation, that is del cross H equal to J. Okay, so we need to check whether this equation holds true even for a time varying case. Okay, so and we see that this particular equation does not hold true for the time varying case, and we require some modification. And that modification itself is displacement current or displacement current density. Okay, so let's begin. So we know that in steady magnetic field, the point form of Ampere's circuit law is given by del cross H equal to J. This is a known fact to us. So next, we know that the divergence of the curl of any vector field is identically 0. Okay. So this is, that is, divergence of a curl of any vector field, okay, should be 0. So if I take a divergence of this, if I take a divergence of a curl of this particular field, that is divergence of a curl, okay, that is should be 0. So which means I should take divergence on both the sides, okay, and hence at the right side is del dot J. Okay. But we know that, okay, the equation of continuity is given by del dot J equal to minus dou rho V by dou T. Okay, so this point we have discussed in the module 2, the equation of continuity. Okay, this is the point form of equation of continuity. Okay, that is del dot J equal to minus dou rho V by dou T. Okay. So now you could really see that the equation number 2 and equation 3 is incompatible for time varying case. Okay. Because now what does equation 2 tells that? From equation 2 it tells that the del dot J is 0. Okay. But I know that del dot J is actually given by this minus dou rho V by dou T. Okay, which is not 0, at least for time varying case. For steady case, it is 0, that is, that's a fine, it's not a big deal. But for time varying case, that is not 0. Okay, if this is del dot J is not 0, okay, which means these two equations are not compatible, which means that the equation 1, which we assume, okay, that it might be true for time varying case, is also not true. So now, what does it mean that we need to really modify this equation number 1? Okay. So now we need to modify equation number 1 in order, okay, to satisfy this particular equation number 3. So I say next thing is, let us modify equation 1 by adding unknown term, and let that unknown term be a G vector. Now I say that the del cross H is J plus G. Okay, J plus G. Now G need to be determined. Okay, we need to define what is this G, and we need to determine. We should define and also we need to determine it. Okay. Now, in order to do that, we'll try to take again the divergence of the curl into this equation. Okay. So again, we'll take the divergence of the curl of this equation number 3. So it is del cross H is equal to del dot J plus, okay, before that, we know that the divergence of a curl is 0 is equal to del dot J plus del dot G. Okay, del dot G. So from equation 2 and 3, we come to know that, okay, we need to modify this equation number 1. And I said that we will modify this equation number 1 by adding an unknown term, that is G, which we need to really define and determine. In order to do that, we are taking again divergence of this particular equation number 3, and that is what we have done it here. Okay. So now, next, what I could say that we know that the del dot J is equal to minus dou rho V by dou T. Okay, and you could see that in order to we get 0, that is, if I really try to check from this side, okay, that is del dot J plus del dot G is equal to 0. I know what is del dot J, which is minus, dou rho V by dou T plus del dot G is equal to 0, which implies that the del dot G is equal to dou rho V by dou T. So I got to know what is the divergence of this unknown quantity which I need to determine, and this given by dou rho V by dou T. Okay. So next thing I say that the rho V is given by del dot D. The rho V is given by del dot D. So next I could say that del dot G is equal to, I'll try to substitute this quantity over here. So dou by dou T of del dot D. Okay. So which means that the del dot G, okay, I can rewrite this as del dot dou D by dou T. Okay. I make a simple substitution, that is rho V equal to del dot D, okay, for this one. And further, I said that this particular thing can be written as del dot dou D by dou T. Okay. So now this equality tells that, okay, G is equal to dou D by dou T. Okay. Dou D by dou T. So you could see that we have determined the unknown quantity, which is the partial derivative of D with respect to the time. Okay. So now, what is the Ampere circuit law? Now you could see that it is actually del cross H equal to J plus G, and G is dou D by dou T. Dou D by dou T. Okay. And this term, the dou D by dou T, okay, is given the name as by Maxwell as a displacement current density, the dou D by dou T, okay, is denoted by JD, okay, it is denoted by JD, and it's given the name as displacement current density, displacement current density, displacement current density. Okay, so you could see that now this Maxwell's equation, okay, is consistent with the other equation, okay, and we call this as modified Ampere circuit law. Okay, this is modified so that it is compatible with the time varying case. Okay, so this is modified Ampere's circuit law. Ampere's circuit law. Yeah. So now, as I said at the beginning, okay, so we were interested to check, okay, I mean whether we need some modification for those existing Maxwell's equation, okay, and you could see that if you try to check the Maxwell's equation, we have two curl operations and we have two divergence operations. One is del dot D, one more is del dot B. One more is del cross E and del cross H. Okay. And out of those four equations, we could see that the first curl equation got modified as curl of E equal to minus 2B by dou T. Okay. And also, also this curl of H also got modified as curl of H equal to J plus JD, and JD is dou D by dou T. Okay. That is displacement current density. Okay. So now we can, once we know displacement current density, we can define displacement current. Okay. So that's quite simple. You could check that displacement current ID is equal to surface integral of JD dot ds, which is dou D by dou E dot ds. Okay, that is the displacement current. Okay, that is the surface integral of displacement current density. Okay. So we got the point form of an Ampere circuit law, that is, as I just now we derived, that is del cross H equal to J plus JD, when JD is dou D by dou T. Okay. So we can also obtain the integral form of Maxwell's equation. Okay. So if you try to see any Maxwell's equation, we have two forms. One is point form and one more is integral form. Okay. So this is a point form of Maxwell's equation, and we can get its integral form of Maxwell's equation. Okay. As I said that it is done by applying the Stokes theorem. So before that, we'll try to integrate over the surface of this equation so that it is del cross H dot ds. Similarly, J dot ds plus dou D by dou T dot ds. Okay. So well, for this left-hand term, we'll apply the Stokes theorem, and we know that the Stokes theorem will try to convert the surface integral to the line integral. So, which means that I can write this as H dot dl, and you could see this is nothing but a current. Okay, this is a current I, and you could see that this is current ID. This is the current ID. Okay. And this is Ampere's circuit law in the integral form. Okay. So that's what about the displacement current density and the displacement current. Okay. So now there is some important point we should really observe. That is a node. Okay. So you could try to understand clearly this particular term J. Okay. That J is conduction current density. Okay. We should make a very clear note. J denotes conduction current density. Conduction current density. Okay. That is that is the what we could say that the current density in a conductor. The current density in a conductor. Okay. Yeah. J. Okay. And if you try to take a non-conducting medium, okay, in a non-conducting medium, the J will be the 0 because in non-conducting medium we don't have any free electrons, and really we cannot define this term conduction current density. Okay. In that case, the Maxwell's equation will be like simply del cross H is equal to J. Del cross H is equal to J. Okay. So with this understanding of displacement, current density and displacement, and one more thing, it should be very clear that the displacement current arises, okay, because of time varying electric field. Okay, because it is given by dou D by dou T. So whenever you have a time varying electric field, because D is related to E by epsilon times E. Okay. So whenever there is time varying electric field exists, okay, the displacement current do exist. Okay. So next, I would like to, so far you could see that we have seen different current or current density. Okay, you could recall that the first thing we saw about convection current, and then we saw a conduction current. Okay. And in today's topic, we saw about displacement current. Okay. Displacement current. We have studied about convection current. Okay. We also know what is about displacement current, and now we saw about a displacement current. Convection current we have seen, and today we saw about the displacement current. These are the three different types of the current what we see. Okay. Yeah. And this displacement current, okay, you will try to see in the capacitor. Okay. So now, the significance of this displacement current, okay, we'll try to show that saying displacement current is equal to conduction current in capacitor. Conduction current in capacitor. Okay. So we are trying to show that the displacement current is equal to conduction current in the capacitor. Okay. So here you will see that, okay, the flow of the displacement current. Okay. And the significance of displacement current is in, is in the capacitor. Okay. Yeah. So let me take a capacitor which is excited with a time varying source, that is V naught cos omega t. Okay. I will take two different scenarios. The same circuit, same, that is, this is same V naught cos omega t. V naught cos omega t. I try to apply H dot dm. Okay. So we'll try to take two different scenarios. Okay. So we take up a capacitor and we excite with the source P naught cos omega t. Okay. And I'll try to apply the Ampere's circuit law. Okay. With a loop. Okay. Shown as here in the figure, and it is bounded by a flat surface. Yes. Okay. It is bounded by a flat surface. Yes. Okay. And yeah. So I'll try to take the same loop L. Okay. But now I'll try to take the surface which is like a balloon shape. Okay. Instead of taking a flat surface, now I'll try to take like a balloon shape. Okay. And the bottom of this surface encloses one plate of that capacitor. Okay. It encloses one plate of the capacitor. Just the same current I. Now I have taken the S prime surface. The surface is this one. The most important is the surface S prime encloses one plate of the capacitor. Okay. Yeah. So in this particular topic, I would like to show that the displacement current is equal to the conduction current in the capacitor. So here we'll try to appreciate the significance of the displacement current when we find its application. Okay. So let's begin with that. So for a figure 1, okay, let us apply an unmodified Ampere circuit law. Okay. So let us apply unmodified Ampere's circuit law. Okay, so it is unmodified Ampere circuit law. So what is unmodified Ampere circuit law? H dot dl is equal to I enclosed. Okay, that is known to us. Modified Ampere circuit law is H dot dl equal to I plus id. I plus id. Okay, yeah. So and this I enclosed, we know that is J dot ds. J dot ds. Yeah. So it means that I am applying this particular Ampere circuit law for this loop as shown here as L. Okay, and that should be equal to I enclosed within that loop. Okay, and that should be also equal to the surface integral of J dot ds. And it is very quite obvious from the figure that, okay, the I enclosed is nothing but this particular I, which is the conduction current, which means that the J is also the conduction current density. So I can say this I enclosed is equal to this I, okay, is equal to this I, which is the conduction current flowing through this particular capacitor. Okay. Or you could say that this is nothing but I, which is flowing current in this particular conductor. Okay. So now from circuit theory, we know that this conduction current I is given by C times dV by dt is equal to C times dV by dt. C times it is C times the differentiation of the potential difference across the capacitor. Okay, and the potential difference across the capacitor is V naught cos omega t. Okay, so I can write now this I is equal to minus C times the differentiation of V naught cos omega t is minus V naught omega sin omega t. Okay, and this is this particular C. Okay, that is a capacitance of. I have taken a parallel plate capacitor. And the capacitance of the parallel plate capacitor can be written as minus epsilon times A divided by D, and hence it is V naught omega sin omega t, and that is equal to this particular. Okay. Yeah. So just I have replaced the C as the capacitance of the capacitor. For a parallel plate capacitor, the capacitance is epsilon time, that is the permittivity of dielectric medium. A is the area of the parallel plate capacitor. That's if you have one more parallel plate here, A is the area of this parallel plate capacitor, and D is the distance between the parallel plate capacitor. Okay, and that is that I current. Okay. Now, what we'll do is, now we'll apply the Ampere circuit law to different scenario. Okay. Now, what is the fact is, we try to keep this loop same. Okay. The loop same, the same loop, but you could see that in this particular case, okay, this is the loop, and the surface was a flat surface. The surface was the surface was like a circular flat surface. Whereas in this case, I have taken the same loop, but the surface is like, you could think like something like extended. You extend, you have extended such a way that, okay, such a way that the surface encloses one plate of the capacitor, as I shown here. It's a correction. Okay. Now, according to an Ampere circuit law, okay, Ampere circuit law, what it says that, okay, we can apply Ampere circuit law to any loop. We can apply Ampere circuit law to a loop, okay, with this same loop with a different surface, okay, same loop, okay, with different surface, such a way that, okay, you can really apply the same loop with a different surface such that, okay, for this every different surface, the perimeter of the surface should be the loop. Okay. So this is known to us from the Ampere circuit law. Okay. But But if I will try to apply Ampere circuit law to this one, H dot dl, my loop is same, but I have taken different surface as S prime, J dot ds, okay, yeah, that should be equal to I enclosed. And if I ask you now what is I enclosed, okay, it is very interesting fact. You could see that. Now I cannot say that the I enclosed is equal to I, because this I is a conduction current which can flow only in the conductor. And as my surface has enclosed one plate of a capacitor, okay, which is, you could see that it has also enclosed a dielectric medium, okay. So this current can flow to here, but it cannot pass through the surface because here you have a dielectric medium. The conduction current in a dielectric medium is zero, okay. So which is zero here. This is contradictory, okay. Because what Ampere circuit law says that, okay, so it says that a closed loop H dot dl is equal to I enclosed, okay. You can really apply the Ampere circuit law, okay, with the same loop for an n number of different surfaces, such that, okay, all those different surfaces should have the perimeter as this particular loop, and that's what I have taken, okay. So according to Ampere circuit law, we should have got the same answer even for this surface or for this surface, because for these two different surfaces the loop is same. The loop is same, okay, but we are getting a different answer. This is a contradictory. Yeah. Now, how we can really resolve this contradictory? Okay. The fact is that, okay, so now I could say that in order to resolve contradictory, or we can say conflict, to resolve this conflict, we need to include displacement current. We need to include displacement current. Okay. Now we know that we have total current density as J plus J, J plus J. Okay. So now you could check that. Okay. In this particular case, okay, the J is the first thing according to Ampere circuit law. So you could see that we have begin with an unmodified Ampere circuit law, and because of that we got this contradictory issue. Okay. We begin with an unmodified Ampere circuit law, and because of that we got this issue. Okay. So if we have taken the modified Ampere circuit law as J plus JD, you could see that this particular thing can be resolved. Now, what I can say that in this particular case, okay, in this particular case with the surface as S prime, okay, no doubt that the conduction current J is zero, but you have the JD exist. Now, I say that this is not zero, but it is JD. That is J. I'm sorry, I should not say JD. It is like a surface integral of J dot ds, and this is actually like ID. This is actually like ID. And here it should be J. And here it should be the J. Okay. Yeah. So now what I need to show is that this ID is same as the I, which just now we have shown that the I is equal to minus minus V naught omega minus V naught omega epsilon A by D sine omega t. If I show that this ID is equal to this much, then we can really say that the displacement current is equal to the conduction current. Okay. And you could also check that the first equation which we had used for this case, that is closed loop H dot dl equal to, we have used J dot ds equal to I enclosed, and I enclosed is equal to I. Okay. And what we say is that in the first case, the JD was 0 because it is a conductor, and in a conductor we have the conduction current. Okay. And hence it is correct over this case. Okay. So what I am trying to tell is, so now if I take my modified Ampere circuit law, if I want to apply Ampere circuit law to this one, which I say that H dot dl is equal to I enclosed, and this I enclosed is equal to I, because this current, which is this current is flowing through a conductor, okay, and this the surface area S encloses this particular current, that is a conduction current. Okay. So in this scenario, okay, the JD is 0, whereas J is present, and hence this is correct. Okay. Whereas while considering this, okay, we did consider the modified Ampere circuit law, and hence because of that we got an issue, contradictory issue. The moment I consider a modified Ampere circuit law, you could say that this is actually equal to ID. Okay. So now all is that I need to show that this ID is equal to this I, which just now I have shown, okay, is equal to minus V naught omega epsilon A sine omega t by d. Okay. So we can do it quickly. Okay. So we know that the d is equal to epsilon times E. Okay. Yeah. So this is D field and this is E field. Okay. So we know that the electric field through a capacitor is really constant. Okay. That is, and this is the fact we have seen that. Okay. If we have two sheet charges and the electric field between them will be constant. Okay. And the electric field between capacitor plate, I mean in terms of magnitude, is given by E equal to V by T. That's quite simple. Okay. V is the potential difference of the capacitor, and D is the distance between that parallel plate capacitor. And this fact also we have seen, I think, in the topic of Poisson's and Laplace equation, because in that particular topic we have tried to derive the capacitance of different configurations. Okay. So the electric field between the capacitor plate is equal to E equal to V by D. Okay. Yeah. So which means that D is equal to epsilon times, and V is nothing but V naught cos omega t by D. Okay. So next, I'll try to find JD. JD is dou D by dou T. Okay. As I said that the JD is always present if you have the time varying D or the E field. Okay. On that time varying field you have here, and there exists the JD. Okay. So now you could say that the JD is equal to, again, minus it's a minus epsilon V naught omega sine omega t divided by D. So this is our J. Now we can find the current, okay, and we could check that this JD is actually constant because electric field is constant, okay, so this JD is also constant. Okay. And if that is the case, we can find the current by simply multiplying the current density with the surface. Okay. So the ID will be equal to JD times the surface area. And the surface area, I have taken the parallel plate capacitor. Okay. So you could see that we got minus epsilon V naught A omega sine omega t by d, that is ID. And you could really check that, okay, ID is equal to I. ID is displacement current, I is the conduction current, okay. And this is, and in fact, this has to be true. Okay, it has to be equal because according to KCL, if I apply KCL at this particular node, whatever current enters here it has to leave. Okay, so you could see here. Here it is conduction current, and here it is also conduction current. So in between this is a dielectric, and in that dielectric we have the displacement current, which is equal to this conduction current. So here is conduction current, and that same current is, here we have displacement current, which is same as this one, and here again we have the displacement current. Okay. And hence you have the closed loop flowing the same current. Okay. So this is all about this, the conduction current and the displacement current. Okay. So as I was telling from the beginning, okay, out of 4 Maxwell's equations, the 2 Maxwell's equations will get modified for time varying case, and the remaining 2 will remain the same. Okay. And hence we say that the 2 Maxwell's equation, that is del dot B equal to rho V, remains the same, and also del dot B is equal to 0. Those are unmodified. Okay. Yeah. Those are unmodified. Okay. So now we are in the position, okay, to summarize summarize the Maxwell's equation for time varying case. Okay. So now we can really summarize the Maxwell's equation for time varying case. Okay. I try to write in the both the form, point form, and integral form, and also I'll try to write some remarks. Okay. So here we have point form. Here we have integral form, and here we have the remark. Okay. Yeah. So the first thing I could recall that del dot D is equal to rho V, which is not modified, it has remained same as same for time varying case and same for the static case. Then next we can write first all divergence. So del dot B is equal to 0. Next thing we have C del cross E got modified minus dou B by dou T. This one has got modified. And the next one is del cross H is equal to J plus JD, and we always, okay, most of the author want to write this JD as dou D by dou D. Okay. We can write JD, but in order to emphasize that it is a partial derivative of D filled with respect to time, we write it as dou D by dou T. Okay. And one thing it should be very clear, J indicates the current density in the conductor. Yeah. And this JD is exist wherever you have time varying D or E field exist. Okay. So now I can write this equation in the integral form. Okay. And I know that this dou surface integral of d dot ds equal to q enclosed, and this q enclosed we can also write it as volume integral of rho v d. Okay, and this we can write it as b dot ts is equal to 0. And this one, we know that it is closed loop line integral of E is equal to minus surface integral of dou B by dou T dot ds. Dou B by ds. This is what we have seen at the morning. Okay. So this is surface, this is line integral. Okay. So next here we have closed loop line integral of h dot dl is equal to I, and I is conduction current, and this is I can write like ID. I can write I plus ID, or I can write this as surface integral of, this is JD, so that is dou D by dou E dot ds. So this is the Maxwell's equation in the point form and integral form. And some remarks we should recall, these equations are from what? This is due to a process law. This is non-existence of monopole, non-existence of monopole. This is because of Faraday's law. That is because of Faraday's law. And this is, we could say, modified Ampere's circuit law. Modified Ampere's circuit law. Modified Ampere's circuit law. Okay. Yeah. So these are the four equations. Maxwell's equation, okay, forms a basic for all electromagnetic theory. Yeah. So the Maxwell has really contributed for this term. Okay, if this term was not, you could say that invented. Okay, if Maxwell was not able to identify this, you could say an additional term which is required in the Ampere circuit law. Okay, then we cannot really write a combined equation for an electromagnetic theory. Okay. Yeah. So, and because of that, okay, we really appreciate more about the Maxwell because this was a great contribution. Okay. And for many years, people do not believe this. Okay, do not believe this because because he cannot show experimentally. Okay, he cannot show this particular JD or ID. Okay, experimenting. Because the fact is that at low frequencies, JD term is very negligible. And at the time of Maxwell, okay, it was not easy to generate a high frequency signal. Okay, so it was Hertz. Okay, okay, where Hertz really was successful in generating a high frequency. Okay, at that time we could able to detect this JD. Okay, and hence the people accepted this particular equation. Okay, and when it was possible to combine the whole electromagnetic theory in this particular four Maxwell's equation, okay, we also predicted that is waves is an electromagnetic in the nature. Okay. That is what we are going to see in the part B of this module. Okay, electromagnetic waves. Okay. Yeah. So this is all about Maxwell's equation, and we will stop today here.